Have you ever wondered how certain compounds distribute themselves between two immiscible solvents? This phenomenon is explained by the Nernst Distribution Law. Welcome to the fascinating world of chemical distribution. Today we will dive into the Nernst Distribution Law, a fundamental principle in the field of chemistry and pharmacy. This law, named after the German physicist Walther Nernst, is a critical player in understanding how compounds behave in different solvents. So what is the Nernst Distribution Law? In simplest terms, it states that a solute, or the substance being dissolved, will distribute itself between two immiscible solvents in a way that the ratio of its concentrations in each solvent is constant at a given temperature. Immiscible, by the way, refers to the inability of two substances to mix together like oil and water. Imagine you have a beaker containing water and oil with a solute added. The solute will partition itself between the oil and water based on its affinity towards each. This is where the Nernst distribution law comes into play, predicting the ratio of the concentrations of the solute in the oil and water phases. Now you might be thinking, this sounds quite straightforward, so what's the catch? Well, like any scientific law, the Nernst distribution law has its limitations. It assumes that the solute doesn't interact with itself or change its form in either solvent, which isn't always the case. Plus, it doesn't account for the effect of ionic dissociation and association, which can significantly alter the distribution of compounds. Why should we care about all this, especially in the field of pharmacy? Understanding the Nernst distribution law and its limitations can help pharmacists predict how drugs will distribute in the body. This knowledge is critical for determining the appropriate dosages of medications, designing new drugs, and predicting potential drug interactions. By the end of this video, you will have a better understanding of the Nernst distribution law and its significance in pharmacy. So, stay tuned as we delve deeper into this intriguing subject. So, what exactly is the Nernst distribution law? Let's break it down. The Nernst distribution law, named after the German chemist Walther Nernst, is an essential principle in the field of chemistry and pharmacy. It's all about how a solute, or a substance that is dissolved in a solvent, distributes itself between two immiscible solvents. Now, what do we mean by immiscible solvents? Well, these are simply liquids that do not mix together like oil and water. Think of it like this. You have two separate layers of liquids, say water and oil, and you drop a solute into this mixture. The solute will tend to distribute itself between these two layers. The Nernst distribution law explains how this distribution happens. In more technical terms, the Nernst distribution law states that at a constant temperature, the ratio of concentration of a solute in two immiscible solvents is constant. This constant is called the distribution or partition coefficient and is usually represented as K. Let's take a simple example. Imagine you have a tea bag, which is your solute, and you steep it in a cup of hot water, which is your solvent. The tea leaves distribute themselves evenly throughout the water, creating a uniform solution. Now, if you were to add oil to this mixture, the tea leaves or solute would distribute themselves between the water and the oil. The proportion of tea leaves in the water to the oil would remain constant, as the Nernst distribution law predicts. So, essentially, the Nernst distribution law provides a way to predict how a solute will behave when placed in a mixture of two immiscible solvents. This principle is incredibly important in the world of pharmacy, as it helps to predict the distribution of drugs in the body. So, in its simplest form, the Nernst distribution law explains how a solute will distribute itself between two immiscible solvents. Like any scientific law, the Nernst distribution law has its limitations. Understanding these limitations can help us apply the law more effectively. Now let's delve into the limitations of the Nernst distribution law. Firstly, it is assumed that the solute does not associate or dissociate in the solvent. This means that the law only applies to non-ionic solutes. However, in reality, many solutes do undergo some level of association or dissociation in the solvent, which can significantly alter their distribution. Secondly, the law assumes that the distribution of the solute between the two phases is at equilibrium. However, reaching equilibrium can take time, and in many practical situations, equilibrium may not be achieved. This means that the distribution of solutes may not always follow the Nernst distribution law. Thirdly, the law presumes that the temperature remains constant throughout the distribution. This might not always be the case, especially in large-scale industrial processes where temperature fluctuations can occur. Temperature can affect the solubility of the solute, and thus, the distribution. Fourthly, the Nernst Distribution Law assumes that the solute does not react chemically with the solvents, but there are instances where the solute might interact with one or both solvents, altering the distribution of the solute. Lastly, the law assumes that the solvents are completely immiscible, meaning they do not mix. But in reality, there's often a small degree of miscibility between the solvents, which can affect the distribution of the solute. These limitations highlight the complexities of real-world chemical systems. They remind us that while the Nernst Distribution Law provides a useful starting point, it does not capture all of the intricacies of solute distribution. Despite these limitations, the Nernst Distribution Law is a fundamental concept in the field of pharmacy and is widely used. It serves as a pivotal tool in understanding and predicting the behavior of drugs in various environments, thereby aiding in the development of effective pharmaceutical formulations. Now let's discuss how ionic dissociation and association can affect the distribution of a solute. When we talk about ionic dissociation and association, we're talking about the splitting of ionic compounds into separate ions and the reverse process of ions coming together to form ionic compounds. But how does this relate to the distribution of a solute between two immiscible solvents? Well, it's all about how these ions behave. In the world of chemistry, ions are like social butterflies. They love to interact with others, and this interaction can affect how a solute distributes itself between two solvents. Consider a simple example. Suppose we have a solute that can dissociate into ions in one solvent, but not in the other. In the solvent where the solute remains undissociated, the molecules stay together as a whole. However, in the solvent where the solute can dissociate, the molecules break apart into ions. What does this mean for the distribution of the solute? Well, the solute will preferentially distribute itself to the solvent, where it can dissociate. This occurs because the dissociation process increases the solute's solubility in that solvent. Now let's flip the coin and talk about ionic association. This is where ions come together to form ionic compounds. If we have a solute that can associate into larger molecules in one solvent but not in the other, it will preferentially distribute itself to the solvent where it can't associate. This is because the association process decreases the solute solubility in that solvent. In essence, ionic dissociation and association can influence the distribution of a solute by altering its solubility in different solvents. This concept has significant implications in many areas, especially in the field of pharmacy, where understanding how drugs distribute in the body is crucial. As you can see, ionic dissociation and association can greatly affect the distribution of a solute. So how does all of this apply to pharmacy, you might ask? Well, let's dive right in. The Nernst Distribution Law, its limitations, and the effect of ionic dissociation and association play a significant role in pharmacy. They help us understand how drugs distribute in the body, predict their behavior in various physiological environments, and even design more effective and safer medications. For instance, consider the formulation of a pharmaceutical suspension. The Nernst Distribution Law can be used to predict the extent to which a drug will dissolve in the suspension medium, based on its distribution coefficient. This is crucial in ensuring the drug's bioavailability. However, remember the limitations we discussed earlier? They come into play here too, reminding us that this prediction is only an approximation and may be influenced by factors such as temperature and pH. But it doesn't stop there. The effect of ionic dissociation and association also comes into play. Many drugs are weak acids or bases, which can ionize in solution. This ionization can significantly affect the drug's solubility, and consequently its distribution and absorption in the body. Understanding this allows pharmacists to manipulate the drug's formulation to optimize its therapeutic effects. Moreover, the principles of the Nernst Distribution Law and ionic dissociation are also applied in drug extraction and purification processes. They help guide the selection of solvents and extraction conditions to achieve maximum yield and purity. So, as you can see, These concepts are not just theoretical constructs, they are practical tools that pharmacists use every day to ensure the safe and effective use of medications. The knowledge of the Nernst Distribution Law, its limitations, and the effect of ionic dissociation and dissociation is indeed a cornerstone in the field of pharmacy. As we have seen, the Nernst Distribution Law and its associated concepts are fundamental to many aspects of pharmacy.